There we go. All right. Other questions about any of that? No? Okay. All right, so we left off on Wednesday talking about heat capacity, right? How much heat certain objects can hold. And that was measuring Q, which is heat. So the next question is, we need to think about the work aspect of it, right? Because we have this equation. Right, we had delta E equals Q plus W, and we talked about Q a little bit on Wednesday. That's what we talked about, heat capacity. Q is heat. And as a review, let me find my picture. Right, we talked about this, that in this case I have reactants going to products. I have an internal energy change of less than 0, which is a negative change, which means the energy is going systems to surroundings. So the sign of the E tells me where the energy is flowing. If it's negative, it's flowing out. If it's positive, it's flowing in. And so if E is related to heat and work, talked a little bit about heat. The question is, how does work change when I have a reaction happen?
Is that the formula that we use for?
That is a equation. That's what we did on Wednesday.
Oh.
All right, so how does work change with volume changes? So, for example, all right, let's say you turn on your car outside, right? And if you're driving it, you're adding gas to the engine. The engine burns the gas, produces carbon dioxide gas, some water gas, a bunch of other steam products. All right, so burning gas creates carbon dioxide gas, as well as some other products, but that's one of the main ones. Gas is a liquid, right? When you put it into your tank, it's a liquid. It's going from a liquid to a gas. The gas takes up a lot more volume than the comparable amount of liquid. And that change in volume pushes the pistons, which then crank your tires on a very generic scale of how a combustion engine works. But in general, by burning gas, you make carbon dioxide gas. That gas needs more space. That increase in volume now has done work. It pushes. That's a work word. So now it's pushing something to drive the car. All right, so this is the equation we're going to use to describe work and volume changes. All right, so looking at this equation here, is pressure or volume changing? Volume, right, because that's the one with the delta. If P is not changing, what does that mean P is? Constant. So this is the work equation as long as you are at constant pressure. All right, so let's say I have my volume increasing. I'm going from, bless you, my volume has changed, I don't know, 100 liters, right? My delta V is 100, and I'm at 1 atmosphere. So is work positive or negative? If P is 1 and delta V is 100. Negative, right? Do you need me to plug that in? -1 times, okay. Does that mean that work has not been done? No. Okay, so if work is negative, it means that work is being done on the surroundings by the system. It means the direction of the work is going out. Just like in delta E, when it's negative, it means it's going from the system to the surroundings. So if work is negative, it means going from the system. I'm doing work of some sort. So why don't we, oh, if you have your calculators, why don't you go ahead and get those out? We're going to need those. And we will use our brand new equation to look at work at constant pressure. Is everybody ready? All right, so I got two problems. So let's say I have a balloon that starts off at 0.2 liters and I inflate it to 0.985 liters in this room, right? So it has an external pressure of 1. I would like to know about the work. Using the equation W equals negative P delta V. So what do I plug in for P? Yeah, -1 atmosphere. And then how would I go about figuring out delta V? Do I do 0.2 minus 0.9 or 0.9 minus 0.2? Yep, right, it's always final minus initial. So what is my final answer for work? What units is that in? Liter atmospheres, right? All right, what do we measure the energy in? If I'm talking about energy, what unit do I use? Typically joules. I want to also measure work in joules. Liter atmospheres happens to be converts to joules, obviously, using this. There's 101.3 joules per 1 liter atmosphere. I don't know how they decided that, but who knows, but that's what it is. So, if I have 0.785 liter atmospheres and I want to convert it to joules, all right, using my snazzy conversion factors. All right, you get negative 79.5 joules of work. Was work done on the surroundings or done on the system? It was done on the surroundings, right? Because I increased the volume of the balloon, which then forced the air around the balloon to move out of the way. So I worked on the air around the balloon to get it out of the way so I could put air into the balloon. That's the kind of part that's kind of hard to think about. Like when you're thinking about doing work on the surroundings, it's usually that I'm moving air out of the way or I'm adding heat to the water or something like that. It's easier when we do it the other way. Do you want to do another problem like this? Okay, let me come up with something. Let's say All right, so let's say I decide to deflate my tire for reasons only known to me. I guess it just says a tire. It doesn't necessarily have to be my tire. I could have been deflating someone else's tire. And I'm outside. It's 1 atmosphere. It started off at a volume of 25.42 and is now down to 9.84 liters. What work was done in joules and who was worked on? All right, so we have the same pressure we had before. So how did I figure out my delta V? Do I do 25 minus 9 or 9 minus 25? Yep, 9.84 minus 25.42. All right, so then how do I get from linear atmospheres to something more useful? All right, I multiplied by this, 101.3 joules per 1. Oh, yep. It's like 1,578 joules. How would I convert that to kilojoules? Divide by 1,000.
So where you won't make in kilojoules?
I'm going to say you're going to want to be, this one only asks for joules, but you're going to want to be able to go back and forth to kilojoules. Because coming up pretty soon, the numbers are going to be gigantic. Sound. All right, so who had work done on it? The system or the surroundings? The system, right? I did work on the system because I let all the air out. Not all of it. Most of it. It'd be pretty flat tire. All right. So now we have all that kind of sorted. The question is, how do we measure delta E, right? We can measure heat using a thermometer. We can measure work if we know the pressure and the volume. But I would like to get at the actual how to measure delta E. So the way we're going to do this is what you're going to do in lab next week. Constant volume calorimetry. So right here I have my system and my surroundings. Right, if delta E is Q plus W and work tells me change in volume at constant pressure, right, I can do work either way. And if heat is a measure of temperature change, specific heat, mass, and that can go either way, and delta E is a combination of those two, I have to know both technically to be able to answer it. So we could, in theory, right, change the volume, find how that affects work, then change all the volumes to find W, and then use my Q and W to find E. 2 variables, 2 unknowns. We could, but we're going to do a shortcut. All right, so if I hold the volume constant, what now is delta V? If I start off at a liter and I end up at a liter, what's delta V? 0, right? So if I hold the volume constant, then delta V equals 0. What would work then equal if this is now 0? I do 0 work. So if W equals 0, what is delta E equal to? Q, just heat. So if I hold my volume constant, just the change in temperature tells me everything about the internal energy. It's a nice workaround, right? So it makes our solving life easier here in Gen Chem until you get to advanced classes, in which case you realize this is really hard to do. But it's a good starter. It's a good starter. All right, so how do we go about setting up a system that heat is the measure of everything else? I'll wait for everybody to finish writing while I get my next slide ready. We're going to use this technique called calorimetry, which its experimental setup measures a change in thermal energy, right, a delta T, between a system and its surroundings, as long as you're at constant volume. So as long as I'm at constant volume, any change in temperature tells me everything I need to know about heat. So we're going to set it up. That the Q of the calorimeter, right, the heat of the calorimetry experiment is equal to which guy is this guy, big C without the little s? All right, there's 2 types. This is just regular heat capacity. In this case, that's the heat capacity of the calorimeter times delta T. So it's the exact same equation we used on Wednesday, but now specifically looking at this experiment. So the heat capacity of the calorimeter times delta T will tell me how much heat the calorimetry experiment had. Bless you. Okay, we're going to make a huge assumption that there is no heat escaping from your apparatus, that the reaction inside might have gotten blazing hot, but you can't tell by putting your hands on it. You will find that that is not correct next week. We're using a styrofoam coffee cup. So yes, this is a bad assumption for our experimental setup. There are experimental setups where you can insulate it so that there's no heat escaping at all. But we're going to make the big assumption that all the heat that is either given off or taken in is just from the reaction and doesn't come in or out of the coffee cup. So we can say this. Any heat that was gained by the calorimeter, right, which we measure by change in temperature, was equal to the amount of heat lost by the reaction. RxN is my abbreviation for reaction. I realize I write it, I don't always explain it. That's reaction. So whatever heat was gained by the calorimeter, which we usually measure using a thermometer, is equal to and opposite to the heat lost by the reaction, which then must be equal to the change in energy of reaction. So, we just have a new snazzy equation. Must mean it's time to give it a practice test, right? That's usually my system. New equation, give it a practice. New equation, give it a practice. All right, so let's say we have this experimental setup. I have 2.09 grams of sucrose. And it is combusted, which means I burned it all up. And the temperature rose from 23.89 degrees Celsius up to 28.45 degrees Celsius. I would like to know what is the change in energy for this reaction, first in kilojoules. We'll save the second half in a minute. And you also need to know that. The heat capacity of the calorimetry. All right, so first thing we need to do is we need to solve this equation, right? Q, C, delta T. All right, so I literally just told you that a second ago, so we'll go ahead and plug that in. How would I go about finding the delta T? 23 minus 28 or 28 minus 23? All right, so let's see what that would be. How many significant figures do I get to keep my final answer? 3. All right, so Q, the calorimeter, is 22.3 kilojoules. How do I go about figuring out delta E of the reaction? Is it equal to this or something else? It's just negative that, right? So which direction has the heat gone? Out, right? It has gone to the surroundings. So whatever the reaction was, in this case, I combusted sugar, and it heated up the air. And so the air was the surroundings, so the air got hot. Yeah.
So mass has nothing to do with...
Because I'm using regular heat capacity. If I was using specific heat capacity, then I'd care how much. Yeah. All right, so that's the end of that part of the problem, right? Delta E in kilojoules. The reason I put the mass in there, oh, Justin.
That 4.90 kilojoules.
Yep.
Is that like?
It is not standard, no.
Okay, so that's just,
Yeah, when you do it in lab next week, actually the first half of the experiment is determining this. Then the second half is determining this.
okay.
Yeah, so either someone has already solved it for you, or they'll have you work it out. So. All right, so I'm in kilojoules here. The second half, third half, is I want in kilojoules per mole of glucose. So how did I figure out how many moles of glucose I had? Right, I have to use the molar mass. How do they go about figuring out the molar mass? Right, so it'd be 12 times 12 plus 22 plus 11 times 16, whatever that is, 144 plus 22 plus 11 times 16. All right, so now I have kilojoules and I have grams per mole, but I want me in kilojoules per mole. So what do I have to do to get in between that? All right, so here I have grams of sucrose. All right, so first you have to find moles, then you can divide. So let's see, what's that turn out to be? Negative 22.3 kilojoules divided by 0.00611 moles. Yeah.
Why is kilojoules negative?
Because it's the opposite. If the calorimeter is positive, then the delta E has to be negative.
Doesn't they limit kilojoules?
Oh, yep, sorry. I started answering a question before I finished writing it. Sarah?
I'm confused though, because both the change in E and the Q-cal is they're both positive. How did the negative come from that?
So if this is positive and this is negative, then the negative sign just tells me which direction the energy is going. So I could have put positive if I was asking about Q-cal, but I was asking about Q reaction. So the calorimeter has gained heat, but the reaction has lost heat. So overall, the energy of the reaction has to be equal to the negative value, right? Because they're both reactions. Yeah.
So if the Q-cal is positive, then the change in energy for the reaction will be negative?
Yes.
Okay.
Yep. Okay. Okay, so let's look at one more topic today, just get started, and then we'll do all enthalpy. We'll have enthalpy Monday. All right, so delta H and delta E, we have a brand new letter, H. All right, so enthalpy is now this new thing called delta H, which is a measure of the heat evolved at constant pressure. So it's similar to what we talked about in Q, right? Q has been heat, enthalpy is also a measure of heat. We use delta H because it's at constant pressure. It's much easier to hold the pressure constant, right? We're all on the planet Earth. So in general, the pressure is right around 1-ish. It's very hard to hold the volume constant for the majority of experiments you want to do. Almost impossible. So we use delta H because it's at constant pressure, which is much easier to control. So enthalpy is the sum of internal energy and the product of pressure and volume. Which is just really a combination of other things we've had, right? Because this is how we measured work earlier. And it's just rearranged some of the variables. This is a measure of Q, and this was E, and so before was the other way. It was E, Q, work. Just a way around that. Pretty much all we do is right, because E is work and heat. P delta V is work. And so enthalpy is just a measure of heat as long as pressure is constant. All right, we will do enthalpy all day Monday, and hopefully, looks iffy, but we'll try and finish chapter 6 on Monday. We'll see. All right, so why don't you guys go ahead and get into your groups. So you guys are already in your groups because you're overachievers like that.
We are.